Hello students. This lesson continues our discussion on transformations of trig functions, but it focuses on the trig functions that are not sine and cosine, which are tangent, cotangent, secant, and cosecant. Plot the graph of the given function without technology. Give the period, domain, and range. Then use technology to confirm your answers. For this function f of x, it's clear that tangent is the parent function. Tangent of x has an asymptote at negative pi halves and pi halves, and then another asymptote pi units in either direction. Tangent of 0 is 0, tangent of pi fourths is 1, and we get this portion of the graph between negative pi halves and pi halves. This will repeat, but I will focus on one period worth as we talk through the transformations. Now, the first transformation we'll focus on is the effect of this 2x here. We can arrive at that by replacing x with 2x. This is a horizontal compression by a factor of 1/2. This will compress all of the asymptotes and all the points of the graph toward the y-axis, and they will all be half as far as they used to be. Now, before I do the compression, I want to point out something about this tangent graph. The x-axis we still call the midline, and its equation is y equals 0. This point of the tangent graph is called an inflection point. Notice that the inflection point is always found halfway between any pair of consecutive vertical asymptotes. So this distance and this distance are equal. If you begin with an inflection point and head toward the right asymptote, but go half that distance, then the tangent graph has a displacement of 1 unit. This will be a key feature for identifying vertical stretches of tangent and cotangent graphs. Similarly, if you go from the inflection point towards the left asymptote but halfway, there will still be a 1 displacement, but downwards. And also recall that both tangent and cotangent have a period of pi units, whereas the other 4 trig functions have periods of 2 pi units. So now if we do the horizontal compression, this asymptote will now be half as far from the y-axis, same for this asymptote. The origin point will still be there. And once again, if I begin at this inflection point and go halfway toward the right asymptote, then the vertical displacement will be 1 unit upwards. Same is true if you go left halfway towards the asymptote, a displacement of -1. And our tangent curve now looks like this. This is cut the period in half, because now we go from negative pi fourths to pi fourths, which is a period of only pi halves. Keep in mind that if you have tangent or cotangent, that the period is pi. But if you do a horizontal compression on either of these functions by replacing x with bx, then the horizontal compression or stretch by a factor of 1 over b will produce a period that is pi times 1 over b. In other words, the period will be pi divided by b. This is a key relationship for calculating the period if you know b, or if you know the period, how to figure out what b needs to be. Now the final transformation is this +1 here that's in the front. The 2x does not need to remain in parentheses, and you could put the +1 after the fact. Just make sure you do not interpret this as 2x plus 1 as the argument. So sometimes it is helpful to keep these parentheses in place, but they're not necessary. And this, of course, is a vertical shift up 1. This will move the entire graph, including the midline, up 1 unit. Notice this preserves the fact that if you start at an inflection point, which is now at 0, 1, and go right toward an asymptote, but go half that distance to the asymptote, then the vertical displacement is still 1. And if you go left towards the left asymptote, the vertical displacement is 1 down. The only thing that will change that fact is a vertical stretch, which has not occurred in this transformation. And then this graph repeats itself forever in both directions. So the period will be, for tangent 2x, that 2 is the value of b, and the period calculation is to do pi, which is the normal period of tangent, but divided by that b. So that gives us pi divided by 2. That is the horizontal distance between any pair of consecutive asymptotes. The domain will be that x cannot be any of the values for which there is a vertical asymptote. Focusing on this asymptote right here, that's located at pi fourths. So x cannot be pi fourths, nor can it be any x value that is 1 period to the right, 2 periods to the right, or any whole number of periods to the right, or any whole number of periods to the left. So if we add n times the period, where n is an integer, again recall that the integers are all the counting numbers, 0, and all the negatives of the counting numbers. And then the period, of course, is pi halves. So x cannot be pi fourths plus any integer multiple of pi halves. And that's how you describe all of these vertical asymptotes. Now the range, if you look at just one portion of this curve, you can see that it goes down forever with one asymptote and up forever with the other asymptote, so all y coordinates are possible. So we can say y is an element of the real numbers, or we can write that symbol in interval notation, negative infinity to infinity. Now let's confirm with technology. I'll graph tangent of x. Notice our x-axis scale. I'm going to change it to be in terms of pi. So under step size here, I'll put pi halves. Again, let's just focus on the middle cycle. The left asymptote is x equals negative pi halves, and x equals positive pi halves. Now let's make the change to tangent 2x, hide the original, cut the asymptotes in half, and let's do the final transformation. The black graph is the green graph shifted up 1. If you want to animate the shifting, change the 1 to a k, add a slider for k, let k vary from 0 to 1, play it once, drag k to 0, and hit play. The new midline is y equals 1. And notice we will cross the graph halfway between asymptotes. So our inflection point is at 0, 1. And if you go right from 0, 1 halfway to the asymptote, then you will go up 1 unit to height 2. So that takes us to the point pi 8, 2. I'm going to delete these asymptotes and show you how you can graph many of them at once. Define a new variable n to be equal to, then use brackets. Let's begin at negative 10, comma, dot, 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 comma, 10. And this just made a list of numbers from negative 10 up to 10 that are integers. So that includes negative 9, negative 8, negative 7, etc. through 0, and then 1, 2, 3, etc. up until 10. So there's 21 numbers in this list. Now we said our domain was x cannot be, and I will say x equals to make lines, cannot be pi fourths, which was one of our asymptotes, plus any multiple of the period, and the period is pi halves. So we can say n times the period, pi halves. And notice, this just made 21 vertical lines for us, all in the correct positions. Okay, let's go to the next problem. Here the parent is cotangent. Focusing on one cycle, cotangent has an asymptote on the y-axis, and then later again at pi. At pi halves, cotangent is 0. And just like tangent, if you go to the right from that inflection point halfway towards the right asymptote, then there will be a vertical displacement of 1, but this will be downwards 1, because the cotangent of 3 pi fourths is negative 1. And if you go left from the inflection point halfway towards the left asymptote, the vertical displacement will be 1, but upwards, because cotangent of pi fourths is positive 1. And our cotangent graph looks like this. Then, of course, this would repeat itself. Okay, the first transformation effect I'm going to do is this reflection, this negative sign. This is a reflection across the x-axis. So our new graph will look like this. Then the final transformation deals with this plus pi over 4 inside the parentheses. If we change x to x plus pi fourths, this corresponds to a horizontal shift, or we call a phase shift, left pi fourths. So I'm going to focus on where this asymptote goes. To go left pi fourths, we would need the left asymptote to shift to that position. So the whole graph is going to shift left by pi fourths units. And then, of course, this repeats. Now, there was no horizontal compression or stretching here, so the original period will remain unchanged. And the original period was pi, which is the distance between any consecutive vertical asymptotes. The domain will be x cannot be this value, which is negative pi fourths, nor any integer multiple of the period in either direction. So plus n times the period, where n is an integer, and of course the period is pi. Of course, you could also make this description by focusing on this asymptote as your starting asymptote, which is at 3 pi fourths. So you could also say x cannot be 3 pi fourths plus any multiple of the period. It doesn't really matter which one you pick as your starting asymptote. And the range on this one will be negative infinity to infinity again. Confirming with technology, here's the graph of cotangent. We do its reflection across the x-axis, and then we shift left pi fourths. If you want to make all the asymptotes, again, create this list of 21 numbers, or you can go more. You can say, for example, negative 20 to 20. That'll give you 41 numbers. But negative 10 to 10 will suffice. And then create vertical lines. We know that x cannot be negative pi fourths plus any multiple of pi. There was no vertical stretching here, so again, notice that if you begin at an inflection point, such as at pi fourths, 0, and go halfway towards the vertical asymptote to the right, that'll take you to an x-coordinate of pi halves, that the vertical displacement will be by 1 unit, upwards in this case. Also notice that all inflection points are always found halfway between consecutive vertical asymptotes. So notice that if you take an inflection point, that it is halfway between the vertical asymptotes that surround it. And if you start at an inflection point and go halfway towards any asymptote, the vertical displacement will be 1 unit, either up or down. Had I then doubled this function, this would be a vertical stretch, creating this graph, And notice from the black inflection point, if I go halfway towards the right asymptote, which takes me to pi halves, the vertical displacement is now 2. It's twice what it used to be. Keep that in mind when we get to a later example. Let's go on to the next page. This time our parent function is cosecant. Also notice I've labeled my x-axis in terms of whole numbers now, instead of multiples of pi. That's because of the effect of this pi x. Now both the cosecant and the secant graphs have periods of 2 pi. So for either of these parent functions, if you replace x with bx, the period will be the original period scaled by a factor of 1 over b. This is a handy formula to use to calculate the period if you know b, or to calculate b if you know the period for transformations of cosecant and secant. Notice it is different than the formula for calculating the period for tangent and cotangent transformations. In these cases, you do pi divided by b because pi is the original period of tangent and cotangent. So when I see this cosecant pi x, let's go ahead and calculate the period up front. Period will be 2 pi, which is the original period of cosecant, divided by that coefficient, which is pi, which takes the period to 2. Now before we do this horizontal compression by a factor of 1 over pi, recall what the original cosecant graph looked like. Cosecant is the reciprocal of sine. Sine begins at 0, 0. It goes through pi 0, which is roughly here. Pi is a little bit past 3, and then completes a cycle by the time we get to 2 pi, which is roughly 6.28, so a little after 6. At pi halves, we get to a height of 1. Pi halves is roughly here between 1 and 2. And 3 pi halves, it gets to negative 1, so roughly in this area. Here's a loose drawing of one period of the sine wave. Since the cosecant is 1 divided by the sine, everywhere the sine is 0, we'll have a vertical asymptote. At pi halves, sine is 1, so the reciprocal of that is still 1, so our cosecant graph will still go through this point, and it will also go through this point, but they will open up in opposite directions following the asymptotes. So here's a graph of one cycle of the cosecant. But this pi x will do a horizontal compression and change the period from 2 pi to a period of 2. So this vertical asymptote represented the end of our period, and that's now going to be compressed towards the y-axis to a position of 2. And this one will be compressed towards the y-axis to a position of 1. So cosecant of pi x will have these asymptotes, so that it can complete one cycle by the time we go from 0 to 2. This horizontal compression will not change the heights of the maximum and minimum points, which were at 1 and negative 1. Furthermore, halfway between asymptotes, so right here at 1/2, in this case, will be the horizontal position of this minimum. And halfway between 1 and 2, which is at 3/2, will be the horizontal position of this maximum point at negative 1. So the final transformation is to subtract 2, which is a vertical shift down 2. So I'll shift one of these at a time. This one here will shift down 2. And this will shift down 2. This point here we refer to as a min because it is the lowest point of its cup shape. And this point here we'll refer to as a max because it is the highest point of its cup shape. There is still a midline, and the vertical shift down 2 moved the midline from the x-axis to this position, whose equation is y equals negative 2. So notice that the relative vertical positions of the min and max, so the min and max are both 1 unit away from this midline, vertically. The only thing that can change these red gaps are vertical stretches, which did not occur here. And then of course this repeats itself forever in all directions. The period is the horizontal distance from one asymptote through an asymptote to the next asymptote, because that includes the full cycle, both the upper and lower portions of this curve. To describe the domain, find any asymptote. Doesn't matter which one you focus on. Let's focus on this one here. So x cannot be 0, and then we cannot go multiples of half of the period. One period to the right takes you here. It skips an asymptote. To make sure you include all the asymptotes, you need to go over half a period to get this one, and then the other half of the period to get that one, and then continue that to get all of the asymptotes. And of course, you do this in both directions. Well, the period is 2, so half the period, 2 divided by 2 is 1. So we don't need to say that, and we don't need 0 plus. So simply x cannot be n, where n is any integer. Notice that's exactly where all the vertical asymptotes are. At x equals 0, 1, 2, 3, 4, etc., negative 1, negative 2, negative 3, etc. Now the range, let's focus on one period. The lower branch goes from negative infinity to a maximum height of negative 3. That negative 3 should be included. And then we do a union, and now let's look at the upper branch. It begins at a minimum height of negative 1, including negative 1, and goes up to infinity. Parentheses on the infinities. Okay, let's confirm this with technology. Again, here's a graph of sine of x. Notice where it crosses the x-axis. will be the vertical asymptotes for the graph of cosecant of x. And the cosecant branches will open up and down away from the x-axis. Following the horizontal compression, we get this graph. At this point, it's helpful to go from pi labels on the x-axis to whole numbers. So click your wrench and change the step away from pi halves. You can just delete it, or you can put a 1 there. For that matter, you can put a 1 for the step size of y as well. Notice where the maximums and minimums are. Notice that an upper and lower branch are drawn over a period of 2, from x equals 0 to x equals 2. Now let's shift that graph down. The midline corresponds to the vertical shift, so it's at y equals -2. And these maximum and minimums are 1 unit above and below the midline. We create a list of integers from -10 to 10, and then let x equal those numbers, and that gives us our asymptotes. All right, moving on. This time we have a parent graph of secant of x, which is the reciprocal of cosine. Here's one period of the cosine wave, or we can draw this portion of the cosine wave. Wherever the cosine is 0, we will have a vertical asymptote for secant, and then the secant will be the reciprocal of this cosine wave, giving us. So here's one period's worth of the secant curve. Now there are a couple of transformations hiding in this argument, 2x minus pi. There's going to be a horizontal compression and a horizontal shift, and the best way to identify them separately is to, within the argument, factor out the coefficient of x. That leaves x minus, and then divide pi by 2. Easy to confirm this is the correct factoring. If you distribute the 2 back through these inner parentheses, you do get 2x minus pi. So this 2 will produce a horizontal compression, and then this x minus pi halves will be a phase shift. Let's focus on the compression first. The horizontal compression will change the period, so the new period will be the old period of secant, which is 2 pi, divided by that coefficient. And that gives me a new period of pi. So these 3 asymptotes here are all going to be half as far from the y-axis as they used to be. And this point will also be half as far from the y-axis as they used to be. Well, this point won't move because it's already on the y-axis. Let's move this asymptote, make it half as far from the y-axis. This one will be half as far from the y-axis. This point will be half as far from the y-axis. And this asymptote will be half as far from the y-axis. And half of 3 pi halves is 3 pi fourths. Your asymptotes should be equally spaced when you're done with this. So this min here did not move anywhere because it was already on the y-axis, but this max changed position. Again, notice the maximums or minimums are found halfway between consecutive vertical asymptotes. So this distance and this distance are the same. This distance and this distance are the same. Recall that the entire period is this distance, which is pi units. It's from negative pi fourths to 3 pi fourths. And if you subtract those, right minus left, that gives you, in this case, 3 pi fourths plus pi fourths, which is 4 pi fourths, which is pi, confirming our period of pi. The midline is currently at y equals 0, and the minimum is 1 unit above the midline, and the maximum is 1 unit below the midline. The only thing that will change these red gaps would be a vertical stretch, or a vertical compression, which is not occurring in this case. And the final change is to take our green function and replace x, so put it in its own set of parentheses, with x minus pi halves. This is a phase shift right pi halves. So focus on one asymptote or one point. You can focus on this asymptote and shift until that asymptote has moved pi halves units to the right. Or you could focus on this minimum and keep shifting until that point has moved pi halves units to the right. That seems the easier thing to keep track of mentally, because that would put us at this point. So making that shift takes us to this location. And then, of course, this graph will repeat itself forever left and right. Again, the domain, find any vertical asymptote. There's one here at pi fourths. So x cannot be that value. And to it, add any multiple of half the period, because adding one period skips to this asymptote. But we want to make sure we get these interior asymptotes as well. And then, of course, the period is just pi, and n is any integer. And the range for this one, the lower branches come up from negative infinity up to a height of -1, include the -1, union, and then the upper branches all start at a height of 1, included up to infinity. Okay, let's confirm this one with technology. Here's a graph of the cosine. Let's change our horizontal scale back to terms, I'll say pi halves. Here's the secant graph. All of its asymptotes will be where the cosine wave is 0. Now we do the horizontal compression, the shift to the right pi halves, create a list of integers from -10 to 10, and then the equation for all the asymptotes. Let's take a look at just the secant function with its asymptotes. If you do a vertical stretching by a factor of 2, in other words 2 secant x, you will see the maximums and minimums will be stretched from their usual heights of 1 and -1 to new heights of 2 and -2. If you do 3 secant x, those heights will be 3 and -3. Here's secant again. Here's half of the secant. The new maximums and minimums are at heights that are 1/2 unit above and below the midline. And if you do 1/2 the secant of x plus some vertical shift, notice the midline shifts with it to a height of y equals 3, but the maximums and minimums are still 1/2 unit above and below the midline. Okay, let's move on to the next problem. Now we are given the graph of a function, and we are expected to come up with a rule. In fact, find rules in both indicated forms for the function that is depicted in the image below. This is clearly a transformation of either tangent or cotangent. Here's one pair of asymptotes, and the horizontal distance between these asymptotes is 4 units, which you can get by doing 3 minus -1. So the right x-coordinate minus the left x-coordinate, that winds up being 3 plus 1, which gives us 4. And since this is a transformation of tangent or cotangent, and no matter which form we try to do, this b is used to determine what the period is. And for tangent and cotangent, that relationship is the period is equal to pi, which is the normal period of tangent or cotangent, divided by that value b. So if we know that the period is 4, we can substitute 4 in for p and solve this equation for b. So we multiply b to the other side and divide by 4. So b has to be pi fourths. And this will be the case no matter which parent function I use. But let's focus on the first one. The next thing I want to do is find the inflection point. The inflection point of this middle cycle must be this location right here, because it is 2 units away from the asymptote on one side and 2 units away from the asymptote on the other side. So it is halfway between the asymptotes, and the inflection points will always be found there. Further, notice that if I go right from the inflection point halfway to the asymptote, so that would be just 1 unit over, that it appears another point on this graph is only 1/2 unit up. Now normally for tangent or cotangent, that would be a vertical change of 1 unit. This suggests that a vertical compression by a factor of 1/2 has occurred. This tells me that A here will either be 1/2 or -1/2. It'll be 1/2 if there is no reflection across the midline, and it will be -1/2 if there's also a reflection across the midline. Furthermore, the midline does pass through the inflection points, and this is at a height of 2. This tells me that the vertical shift is up 2, so k is going to have to be 2 in this position. Now, if we're starting with the parent graph of tangent, then the curves of the tangent function increase from left to right, just like these curves do, increasing from left to right, which means that we have not had a reflection about the midline, meaning that I want to use a as positive 1/2. So at this point, let's fill in what we do know. A has to be 1/2, and then we have the tangent of b has to be pi fourths, and then parentheses x minus h, and then end both sets of parentheses, and then plus k, and k is 2. I'm going to graph this without the h to see what phase shift would be necessary to produce our graph. Here's the original graph of tangent of x. Let's change the period by replacing x with pi fourths times x. This makes the period become 4. So I'm going to change my x scale and step sizes of 1. So here's my new graph with the asymptotes displayed. Currently notice that the point we're going through is 1, 1. So if I start at the inflection point and go right 1, which is halfway towards that asymptote, we would wind up going up 1. I want this relationship to be go right 1 and go up only 1/2. So we need the vertical compression by a factor of 1/2. And now we have that relationship where from the inflection point, I go right 1 and up 1/2. Now let's do the vertical shift up 2. So the midline goes with it, and we have the inflection point at 0, 2, and that other critical point at 1, 2.5. So again, from the inflection point, go right 1 and go up only 1/2. Now we compare this graph to this graph where we have an inflection point at 1, 2, which means the entire graph needs to be shifted right 1. And to do that, we replace the x with parentheses and x minus 1 in those parentheses, and then I shifted my asymptotes and my points over, and now we have the graph that we are looking for. So we graphed this without a phase shift, and we determined that a phase shift to the right 1 was appropriate, so that x becomes x minus 1. Now let's do something similar with the cotangent. If we have a is 1/2, cotangent, b will have to be pi fourths again, and let's do no phase shift, but a vertical shift up 2. We'll graph this. Here's the original graph of cotangent. Let's adjust the period. Now notice that the curves are decreasing curves from left to right. We want those to be increasing curves, so we will need to do a reflection about the x-axis, as well as a vertical compression by a factor of 1/2. So we actually need our lead coefficient to be negative 1/2. Now we do the vertical shift, which brings the midline with it. And now notice we want that point of inflection, which is at 2, 2, to be shifted left 1 unit to get to 1, 2. So if I replace x with x plus 1, we wind up with the desired graph. So we actually have to use this negative 1/2 for a for our cotangent function in order to get the curves to be increasing curves. So negative 1/2 in front of the cotangent. And we graphed without a phase shift, and notice that to complete the graph, we have to shift left 1 unit. So replace the x with x plus 1. Okay, let's move on to the next one. Find rules in both indicated forms for the function that is depicted in the image below. This time it is clear that we are working with either secant or cosecant as a parent function. Also notice that a minimum is on the y-axis, which is true for the secant graph. So it should be the case that if I use a secant parent graph, that I will not need to do any phase shift. Let's begin by finding the asymptotes. And then one complete cycle will include an upper portion and a lower portion. So the period spans this horizontal distance, which can be found by doing right coordinate, which is at 3 pi, minus left coordinate, which is at negative pi, and that gives me a total of 4 pi. Furthermore, the b in both these cases will contribute to the horizontal compression or stretching, so will be used to determine the period, and the relationship is that the period is equal to 2 pi, which is the normal period for secant or cosecant, divided by b. Now we know we want the period to be 4 pi, so multiply by b and divide by 4 pi, and simplify this, the pi's cancel, and we get 1/2. Now notice that we have a minimum at height 4 and a maximum at height -2. The midline will be halfway in between these heights. You can average 4 and -2. We get 1, which means that k is 1 for a vertical shift up 1 unit. This minimum is 3 units above the midline, and this maximum is 3 units below the midline. This means that there is a vertical stretch by a factor of 3, because normally those distances are 1 unit, which tells me that a needs to be 3 or -3. We can assume that a will be +3 and then later adjust if necessary. So looking at the first case, let's assume a is 3. We know b has to be 1/2. Let's assume h is 0, in other words, no phase shift yet, and then k was +1. Graphing this in Desmos, here's the graph of secant. Let's do the horizontal stretch by replacing x with a 1/2 x. Zoom out a little bit. Notice the asymptotes are already in the correct place. The period is 4 pi as expected. We need to now move the maximums and minimums from 1 unit away from the midline to 3 units away from the midline by doing a vertical stretch by a factor of 3. So multiply the secant function by 3. And then finally, we need to move the midline up 1 unit by doing a vertical shift up 1. And now everything is in place. No phase shift will be required. So no phase shift is necessary. Let's assume we started with the cosecant graph. Again, we need to do a vertical stretch by a factor of 3. The b has to be 1/2. Let's assume no phase shift for the moment, and the vertical shift is up 1. Graphing this in technology, and we have this curve. Notice that we have a minimum at pi 4. Well, we need that minimum to be here at 0, 4. So if I take this graph and shift everything left pi units by changing x to x plus pi and adjusting my asymptotes, and we wind up with the desired graph. So we get 3 times the cosecant, and notice I did not need to use a -3. 1/2 times and replace x with x plus pi, and to both parentheses, and then +1. Now if I remove that phase shift and had used the -3 coefficient, then this result has a minimum at -pi 4, which I could then shift to the right pi units by putting minus pi in the parentheses. So using a -3 coefficient would require just a different phase shift to get the graph to be correct. Of course, I could have also focused on this minimum at 3 pi, 4, and if I shift this graph left 3 pi units, it'll take it to 0, 4. So also I could shift left by 3 pi by adding 3 pi. And this also produces our graph. Really, there are infinitely many ways that you can do this, because you can continue now to shift this graph either left or right by any integer multiple of a period, and you will wind up producing the same graph again. So there are lots of ways to do these kinds of problems. Okay, and this concludes our discussion on doing transformations of the other 4 trig functions.